Let me start with acknowledging my two collaborators, Michele Coghi and Franco Flandoli. And this is, I will try, it's pretty long, but I will try to be concise here. And this is a mean field result for some vortex filaments, and they are related to the 3D Euler equations. And I think I should thank Pierre Germain this morning.
Excuse me.
Yes?
I don't see the PDF. I see just a blank screen. I don't know if other people have the same problem.
Is it? Let me stop sharing and sharing again, maybe?
Yes, I could see it until you started speaking, but then it disappeared. I don't know if other people have this problem.
Let me just, okay, let me.
Yeah, there, now I see it again.
Maybe when I did, okay, let me full screen mode. You tell me if you still see it.
Okay. Now it disappeared for me. I don't know. So yeah, so Catherine is also shaking her head.
So she is.
No, I don't see anything now. It's
yeah. So when you go full screen, it disappears.
So she said I had also this problem. Okay, let me understand. So why is it? So let me stop sharing. What shall I do? Maybe I should.
Yeah, if worse comes to worse, it was okay in the non-full screen mode. It wasn't perfect.
Yeah, why is it so? I opened it with the PDF, right?
Yeah, let's see. Is June here? June, can you give advice?
I'm here. I would say now that you've stopped sharing, I would say share it again. And let's try it again. Sometimes it's just a simple.
Wait a second. What did I do? I didn't share yet. Okay, wait. I have to. Let me share the PDF file, right?
Yes.
I am sharing, and now.
No, it's okay.
So now we can see it. So try it again.
So it is just full screen mode, right?
Yeah.
Yeah, probably because I see something. Why is it saying this? So what shall I do? Maybe I should.
Are you on a Mac?
I am on a Mac.
Sometimes it has to do with the permissions in the Mac.
Do you want me? Okay, let me share now.
Work if you do it in the non-full screen mode. That would be, not ideal, but functional.
Yeah, and we can make our Zoom meeting. Everyone who's watching, we can make it full screen and make a.
Oh, this is good.
Yes.
Good.
Okay, because I had to do it in the full screen mode.
It's perfect now.
But now I cannot move. Okay, let me. Okay. Oh my God. Sorry.
There.
Okay.
Thank you.
So it works, right?
Yes.
Yes.
Okay, very good. So let me go through an introduction. Although Pierre Germain this morning helped a little bit introduce the problem. So the equations that describe the motion of an ideal inviscid incompressible homogeneous fluid in Rn, usually, and in dimension 2 or 3, are given by the Euler equations, homogeneous equal to 0, with divergence equal to 0, and initial condition u in T0 equal to u0. If I denote by xc the curl of the velocity, then the fluid in R3 has the following energy, because I am going kinetic energy. I'm going to use it. So in terms of energy, in terms of velocity, it is described by 1/2 of the norm of the velocity square. And if I rewrite it in terms of the vorticity, it's going to be given by the double integral 1/8 pi, the double integral of the vorticity at the point x, multiplied by the vorticity at the point y, divided by x minus y, the distance. This is the Euclidean norm. And formally, at least, because it's not completely defined. Formally, the energy is conserved. Okay, now if we rewrite the equation, the velocity equation, in terms of the vorticity, in dimension 2, it is a pure transport where the vorticity is transported by the vorticity field, while in dimension 3, you have the vorticity equation, so the transport equal to this extra term that makes all the problematic, as shown this morning by Pierre Germain. And this, as I said before, in dimension 2, the vorticity is conserved, and there are even infinitely many quantities that are conserved. But in dimension 3, the vorticity is not conserved anymore, but rather this gives you the effect of the stretching, if we talk about, vortex filaments. Let me mention here the Bilcatomida, the 84 Bilcatomida, which gives like a condition for the maximal time, if T star is a maximal time of existence for smooth existence of solutions for the 3D Euler equation with finite energy, if and only if this condition is satisfied. It's a criterion to continue the local solution for Euler equation. So the vorticity, the norm of the vorticity in L infinity somehow has to be conserved. Okay, this, as I said before, since I am going to really focus on vortex filaments, let me say something about numerical simulations. Some numerical simulations, in fact, suggest that the region where the vorticity is large have a filament shape. Vincent Meneguzzi discovered numerically that these quantities, these geometric quantities in turbulent fluid. And in my research with Franco and Michele, we were interested in modeling a vortex filament, and then maybe talk about the dynamic of these vortex filaments, and then maybe link them to the 3D Euler equations. This approach, so this is the picture that Meneguzzi and Vincent Meneguzzi had by simulating some turbulent flows. This structure are really the level set of the vorticity. So you see that they are like spaghettis, and they can be long, they can be short. This is where, at least numerically, this is where the vorticity for turbulent flows are concentrated. Let me, before I go through, let me just say something about, the approach that I am taking here. So the approach that Pierre Germain this morning was talking about is to take a vortex filament, pure vortex filament, and to not mollify it. And in this way, he had to somehow mollify the equation using the vorticity, using the viscosity, and to prove that this vortex structure, some of them, can be solution for the Navier-Stokes. And he proved some kind of well-posedness for this Ozine vortex. Okay, my approach will be different. My approach will be to prove that these vortex structures, I'm going to mollify them, and I will prove that they can approximate somehow the pure Euler equation. It's an approximation using a mean field theory. Okay, so let me maybe give some all the results in the 2D. As a lot of people know, 2D is pretty much understood somehow. So deterministic particles. So in the case of when the particles are points instead of filaments, so for example, Dobrushin in 79 gave, he was interested in these particles. This is the dynamic of particles. He takes n of them, and this is K is a kernel. He was interested in the Vlasov-Poisson equation instead of the Euler equation. So he takes a K to be a kernel, a bounded Lipschitz continuous map. And then he defines the empirical measure Stn which is the sum, it's really the empirical measure, deltas. And he proves that if S0, if the initial, so at time t0, if the initial probability measure here weakly converges to a probability measure mu0, then the STN at time t weakly converges to a measure valued mu t, and which is going to be solution of the mean field, which is the PDE. Okay, this is the PDE mean field associated to the measure, you know, the limit of this measure mu t STN. Propagation of chaos, he proved some kind of propagation of chaos in the sense that each particle xt in the limit when n goes to infinity behaves like the solution of this equation, where k is, or where the mu, excuse me, is the mean field solution of the PDE. Okay, so this one, and as you know, the theorem that he proves is that if the initial particles x0 in are IIDs with the same distribution mu0, then the marginal, so there is really propagation of chaos, the marginals, you know, so the distribution of xt1, xt2 in general, it will converge when n goes to infinity, will converge to the product measure mu t phi mu t psi, where mu t is the law of xt, solution of this mean, the curve, you know, the mean field curve solution. Okay, so Marchioro pulvirenti, they are, you know, for stochastic particles with independent noise. This, there was a lot of work by Marchioro pulvirenti in 82, Osada in 86, Schnitzmein in 89, and Jorge Mischler in 2014, where they consider the again, they consider these particles that are points. They consider this kernel K, and they add a noise, an additive noise, independent additive noise. For each, these are n equations, you know, and then they prove, in fact, that if they consider the empirical measure associated to the point particles xti, they prove that STN converges in probability to a measure valued mu t, solution of the Navier-Stokes equation. This is really the Navier-Stokes equation. This diffusion comes from, it's a result of the noise, the additive noise here. This was in 2D. So Michele Coghi and Franco Flandoli in 2016 had, you know, made another result where instead of using an additive noise, they used a multiplicative noise, Stratonovich, and it was correlated. So there was no independence, so there was correlation. And the result is that, in fact, they prove some kind of a mean field to an Euler equation, which is stochastic, 2D. This is 2D. Actually, in their case, they took point and they did it in RD, very general dimension. So they take the empirical measure STN to be given by the following summation, and then they prove that STN converges in probability to a measure valued mu t, which is solution. If you look at this, it is solution, a very general PDE, but if you take that K is divergent free, this is the Euler, the 2D Euler equation with a multiplicative noise in with the Stratonovich, the Stratonovich-Ito noise, multiplicative. Okay. So these are all the results that are known in the literature in terms of mean field, and they were all using particles. So far I didn't.
Did you say things about the regularity hypotheses on K?
I am going to say, of course, in 2D, actually, in 2D, K is not regular. I mean, you do it in two steps. You start with regular, but then you get rid of the regularity in the second step. Good point, exactly. Yes, I will say for the 3D, it's crucial. So, as I said now, mean field result for vortex filaments that are known so far. So these the previous results are dealing with point particles. So they are all xt that are in RD. Filaments for us are curves. So they are curves. So you have a parameter from 0, 1, which will be the arc length of the curve with values in R3. I will do it also in RD, but it will be a curve. So we didn't see any results that are known in this direction. At the level of Gibbs measures, there was a big result by Maida and Jons in 2000, where they dealt, in fact, with parallel filaments, and they proved a mean field result, but the connection to the PDE was absent. Actually, they connected it to a kind of a Schrödinger equation, but it was pretty, it's not, for sure, it was not Euler. A similar result has been proved with the stochastic filaments by myself and Flandoli just after my thesis using Gibbs measures, but it was really, you know, the mean field, we proved it, but the mean field was really implicit. We didn't have a PDE. It was an implicit solution somehow. So there was no PDE involved. At the level of dynamics, no results are known so far. Okay, so let me, although I am let me check my time. Okay, so throughout we will consider the singular kernel K, which is from R3, which is with values as a matrix, which is given, it's really the Biot-Savart kernel, the 3D Biot-Savart kernel, and it is given by the following, and we will regularize it. I will take a mollification of K delta. I will take the convolution with a rho delta, and this rho delta, I will give it even more explicitly later. So, because the true Biot-Savart kernel is really singular, and the singularity is of order 1 over x squared. So we don't know how to deal directly with the singular kernel. This we have to first mollify and then maybe take out the mollification. Which means that actually, if I can do it in the very general setting, I mean, even for any kernel, we can just take any kernel of class uniformly. So they are continuous of order 3, but uniformly, and they are bounded. All my study will be done for very general setting. For actually, even to have even global solutions, I need even more regularity. I need K to be even analytic and with compact support. So we need a lot of regularity. Okay, so what I was trying to say is that we are going to consider curves. These are curves that are C1. And if I use really the kernel, the Biot-Savart kernel, I can vortex filament. I can write the equation for n vortex filaments. I call them gamma Ti n. So since they are filaments, these are maps that depend on time and sigma with values in R3. And this is the interaction between the filament I and the filament J. And this is the derivative of the filament J. So we consider this as actually, in a certain sense, we are going to consider the vorticity concentrated on these filaments, like delta functions. But, you know, like, but since they are filaments, we have to consider them as an integral with respect to this. This is the arc length, okay? Alpha Jn for the moment is just a sequence that converges to 0, but later I will take it to be 1 over n specifically to have the propagation of chaos. Then, since I am mollifying this with the delta, somehow the mean field limit that I'm going to get is going to be the mollified Euler equation in vorticity formulation, where I have this is the velocity. So if K delta is divergence free, I will just have K delta convolution with Ct, gradient of Ct in this pure transport. Okay, so if ut is the velocity field of the fluid and Ct is the curl of the the vorticity, we have that the filament is transported along the flow, right? And this ut I will just substitute by the Biot-Savart flow K delta convolution with Ct. So Ct is concentrated on the curve. As I said, I will just show you the ideas here. As I said, I can do it for a very general K delta, but later I will focus on the Biot-Savart kernel. Okay. So the spaces that we are going to consider now, so the vorticity that I'm going to consider are measures. Vector value distribution, somehow one current vector value distributions. And so I am going to work in the space of the dual space of continuous and bounded functions from Rd into Rd. As I said, I can take D very general. And then the metric associated to this, this space is the supremum. This is somehow the strong norm associated to M. However, my study doesn't go through if I use the strong norm. We have to go to a weaker norm. So we define another norm, as the topology, weaker topology, and the topology that we are defining is the weak topology using the Lipschitz functions theta. Okay, so we are going to use this norm to be the sup over all thetas that are Lipschitz and the supremum over xc theta. This norm, this new norm is weaker than this one, but it is meteorizable. So if I take the unit ball with this, here I did a mistake. So what I'm saying is that if I take bounded sets with this norm, it's a complete metric space. I can use, so bounded balls endowed with this metric, I call this metric, is a complete metric space. We have, nice properties. Now, we have to define, because I would like to go from a Lagrangian, from somehow the Eulerian description to the Lagrangian description. So I have to have a relationship between the two. So let us define if phi is a map, a C1b map from Rd into Rd. We can define the backward, the push, I called it push forward, but actually it's a backward, it's push backward for if theta is regular. If theta is a continuous bounded from Rd into Rd, we define the backward, the push backward of this theta as being equal to d phi, this map, which is going to be related to the Eulerian, the Lagrangian description, theta of phi x. This is like the stretching. Now for the measure xi, for the distribution xi, we will define the push forward applied to a test function theta. We define this push forward as being the xi applied to the push backward of the map theta, which is regular. This is how we define the push forward. Okay, so now there is the Lagrangian current dynamics. So we are going to study the ordinary differential equation dx over dt, which is related to the curve for every curve. So I take one as an example. So dxt over dt equal to k delta convolution with xt applied to xt. This one, if we take k delta to be regular, we'll have a solution, everything is fine. So we can define the flow associated to this equation. And this flow is a flow of diffeomorphism. And with this flow, we then define the Lagrangian description of the vorticity xt as being, in fact, the push forward of the initial condition, xi0. So this is how we define. These two equations now is a closed system. So the pair of equation 2, 3 defines a closed system for Xt, and we can prove that it has a unique solution. The difficulty is there. Okay, so what I would like to do is that this flow equation, I have to prove existence and uniqueness for small t using a contraction map. Then I will prove that this Lagrangian description is equivalent to the Eulerian description. This is the correspondence between the flow map and the PDE. And I will, then describe it for the particular case of the filaments in the sense of K delta to be related to the Biot-Savart law, because here I did it for a general setting. I will prove the continuity with respect to the initial conditions. Then I prove the propagation of chaos for random initial conditions. I will say something about global solutions. In fact, we are able to prove global solutions for the mollified, still for mollified one. And now I have to go to the Euler equation, the 3D Euler equation. I will show you this step. And maybe the stochastic case, I will not say anything. Okay, so as I said, we have the flow, the Lagrangian, we have the Lagrangian description and we have the Eulerian description. And we would like to prove that they are equivalent, in fact. So as I said, the Eulerian description is given by the PDE. So we would like to study this equation where the K delta here, it's mollified. Okay, so we say that this is for Xi, which is a measure, the distribution, not regular. So we say that Xi, which is continuous with values in M, is a current valued solution for the PDE. If you can test it for a test function theta, which is C1b, RD, and RD, you can write it in the variational formulation. You can write it in the variational formulation. It's given by this. And we prove that given Xi0 is a measure in the space that I gave, I took it, the currents Xi0 is in M, on a sufficient time interval 0 capital T, there exists a unique current valued solution for the PDE4. We can prove this. The proof consists, in fact, in showing that Xi, which is on the interval 0 T, which depends on the initial condition, is a current valued solution for the PDE if and only if it is a solution for the flow equation. So we have to go, so we prove that there is a solution for the Lagrangian formulation. The solution is local in time. That solution, we prove that it is also solution for the PDE. And once we have it for the PDE, then I have to prove that any solution for the PDE is also solution for the Lagrangian formulation, the vice versa. They are completely equivalent. And once they are equivalent, then we can go back to prove the global solution. Okay, so this is just to show you how we prove it, So to prove the solution from the Lagrangian formulation is also a solution for the PDE, it is enough just to compute the derivative of the flow map. The converse is a little bit more technical because we have to regularize the solution of the PDE using, commutators, estimates, etc., and then, pass to the limit. Okay, so they are completely equivalent. Now, once they are equivalent, this means that you can work with the Lagrangian formulation or the Eulerian formulation, the PDE or the flow map. Okay, and now the second step is to prove actually that the solution that we found is global in time. So the solution of the Lagrangian formulation is global in time, but in order to do this, we need to control this weak norm of the vorticity in the Lagrangian formulation. And in order to do this, we will use the PDE. And the way we do it is that we have to control this norm. Once you control the norm, then you can continue the solution, your maximal solution. So in order for you, I would like just to show you that the norm of the vorticity or the current, our current, the weak norm is given by the following formula using the push forward. And if you look at the push forward, in order for us to control the norm of this guy, it is enough, it will be enough. I go back to the flow map, the Eulerian dynamic. It is enough to control the norm of the gradient of U somehow in the L infinity norm. In fact, this is all we have to do. And in order to do this, so this is what we have to control. And in order to do this, we need a little bit more regularity on the K, the kernel that we have. So we assume that if the Fourier transform of K has compact support, then the L infinity norm is bounded by the L2 norm, which is not obvious, in fact, because usually it's not true. But this is one step. Once we have this, then we use the PDE to prove that in the case of if C is L2, then we can prove that this the energy is conserved somehow. And once you prove that the energy is conserved, then you have global solutions. You can control the norm that I showed you before. So as a corollary, if K hat has compact support, then all the previous results that I showed you before are global in time. So we have global solution. Okay. Now, continuity with respect to the initial condition. If we have to, in order for us to have the mean field limit, if I take two initial conditions, Xc0 and Xc0n that are measures in M, such that Xc0n minus Xc0 converge to 0 in the weak norm, then on the same time interval, and we know that you have existence and uniqueness for the flow map for this one. So I take the Xc and the Xcn associated to these two initial conditions. Then automatically the supremum of Xtn minus Ct is less or equal than a constant C, that the norm of the difference for the initial conditions. Okay, so it's really a continuous dependence with respect to the initial condition. I will show you later that this constant actually depends on the delta, and I need explicitly the dependence in delta in order for us to pass to the limit to the Euler equation. Okay, so this study, until now, I didn't use the fact that K delta was really the Biot-Savart kernel. Since I would like to go back to the Euler equation, everything that I said so far is true for any kernel K delta which is regular. And now I'm going to use it. In fact, if my kernel is really the Biot-Savart law, so here from the flow to the curves dynamic to vortex filaments, mollified, of course, then here we prove that in fact they are equivalent. So if I have a solution for the flow, the curve dynamics, the flow of the curve dynamics, Xt is also a solution for the PDE, the Euler PDE, mollified Euler PDE. And this theorem is just to tell you that we prove it by hands. Okay, it works also for the particular case of the Biot-Savart kernel. The mean field result, the same thing. We are going to prove that in fact now, if we take curves gamma 0 in sigma that are a family of C1, they are C1 curves. If I take a family of curves like this, and I assume that the Xc0, the associated current at time 0, is concentrated on these curves, defined like this, and if we assume that Xc0 and converges to Xc0 weakly, on the interval 0 capital T, we have proved that there exists if we prove that there exists a current valued solution Xt for the PD with the initial condition Xc0, and we have C1 curve associated to the current at time T, solution of the filament equation with associated gamma 0 in given by the previous theorem. If we define this Xtn as the curves at time T, the concentration of the vorticity at this current at the curve at time T, then Xn converges to Xc in the space of continuous with values in the measure with the weak topology. So you have convergence of the Xn to the solution of the mollified Euler equation. Moreover, we have a mean field we have a mean field theory, in the sense that we have really a mean field theory. Each curve becomes closer to the solution of the equation. So the mean field curve is given by the equation given by the mean field solution. This CT is the mean field solution of the PDE when we pass to the limit. This is one curve. So this is the mean field curve equation. This one has a unique solution corresponding to each initial curve gamma 0 I. And we prove that any curve, actually we prove this. So gamma TIN will converge to gamma TI bar, so the mean field curve here, when n goes to infinity. And this is uniform here. You take the supremum over all t and all sigma, and this is 0. So you have a mean field result. And maybe the last result for the general case, for the K delta mollified, you have also propagation of chaos. So if we take the family gamma 0 to be random variables, so they are C1, 0, 1 in RD cross in RD. And if you assume that Xc0, the current Xc0, we assume that these are random. We assume that they are exchangeable. We don't need independence. We just use the fact that they are exchangeable. We need the fact that they have to be bounded uniformly in, each of them is bounded uniformly in omega, in I and n, almost everywhere. And we need that the initial Xc0 is also bounded. And if the limit, the initial vorticity, at least in expected value, converges to Xc0, then we can prove that we have propagation of chaos, in the sense that the distribution, the joint distribution of these curves will converge to the product measure associated to the mean field curve, the XCT, which is, you know, the distribution associated to the mean field curve. Okay, so now I would like to go to the 3D Euler equation. I have to be more specific. So now we take a mollifier. We have to choose a mollifier rho delta to be the usual mollifier. So I have to write it down. And now we assume that this this function rho, it has a Fourier transform that has a compact support. Okay, and we said that the K delta is rho delta convolution with K. As a consequence, if I look at the norms, I need specific norms now. This K delta, of course, has all the nice property of regularity, K delta. But on top of that, the derivative, the m+1 derivative of this K delta, for example, the highest one that I'm using, I will define it as I define this constant that will depend on delta. I need this dependence explicitly, and this will behave like 1 over delta to the power 4 plus m. As a consequence, so because this mollifier, I will have to have some norms that depends on this C delta. If I take, so the properties of this kernel with the estimates, we have to write them all explicitly in terms of this constant C delta. And in fact, the highest is the C delta 2. If you look at this, I mean, these are just, you do them by hands using all the properties that we did before. And now I focus, this is the equation, the mollified Euler equation that we have, where this V delta is just given by, the velocity is given by the K delta convolution with Xi, the vorticity, where the K delta is the mollified as I wrote it before. We can, I mean, this is known results. If we take the initial condition for the mollified Euler equation or the Euler equation, even for delta equal to 0, if Xi0 delta is in HS with S bigger than 3/2, then we have a local solution, and the solution, the local solution, so there exists this T0, such that on the interval 0, T0, Xi delta is in HS, S bigger than 3/2 strictly. And the supreme moment you have a bound, a uniform bound in delta. on the norm of Xi delta, the mollified vorticity. As a result, as I said before, if I take, now I have to rewrite things carefully for this Xi delta. If we take a delta and R positive, we can find a constant, an explicit constant that we have to write down explicitly. So we have to make sure that Xi0 is bounded by, so it's in a ball. Xi0 delta is in a certain ball. We have like again, this is the continuous dependence with respect to the initial condition, but this constant has to be rewritten very carefully. So we know that the solution exists globally in time, and we have that the supremum over 0t is going to be less or equal. So the difference between the two is going to be less or equal than this C delta, the norm of the difference between initial conditions. This C delta depends on delta C delta 2, so 1 over delta to the power 6, R and T. Moreover, if Xi delta 0 converges to Xi, if I take delta go to 0 in the L2 norm, then Xi delta converges to Xi in the L2 norm, again, on the same interval. Moreover, as a consequence, we have also that the norm of Xi delta, if Xi delta converges to Xi in the measure norm, in the weaker norm, we also have that Xi delta converges to Xi in the weaker norm. Okay, so this is like the stability, it's a stability requirement. And now our main result is the following. So now assume that you have a Xi0 and a sequence of currents, and Xi0 is in HS, solution of the Euler, so this is the initial condition, Xi0 is in HS, S bigger than 3/2. Xi0 is the initial condition of the true Euler equation. And we will assume that the limit of this Xi0, so we can approximate any function in HS by a sequence of currents. I will show you an example. We can always do this. The set of Xi0s is not, Xi0s n is not empty. So assume you have this condition. Assume that let Xt be the solution in HS of equation of the true Euler equation on the interval 0t0 with the initial condition Xi0. And then for every delta and positive integer n, let Xtn delta satisfy the flow, the Lagrangian formulation, the flow map. So Xtn delta is on the interval 0t will satisfy the flow map with the initial condition Xi0n. And now I will assume that in fact this Xi0 and Xi0n also are bounded in the measure norm. They are bounded by R, and we will choose this delta n, not any delta n. We are not able to do it like just goes it to 0. This delta n has to depend in n. We will choose it in such a way that C delta n R multiplied by the initial condition Xi0n minus Xi0, the whole thing has to go to 0. So there is a dependence between delta and n. Then if this goes to 0 with the appropriate rate, then we can prove that the limit of the solution of the true Euler equation, you have a mean field, you have a limit, the Xn n delta, the solution of the flow map, this one will converge to the true Euler equation. Just to finish here, I have maybe 2 minutes. I will just show you, because this, let me go back to this, the main somehow result. This is, we have to base ourselves on the fact that any Xi0 in HS, you can be approximated by a sequence of currents. Okay, so we have to make sure that we can do this. As an example, I'm going to show you this lemma. This lemma shows that the set of approximation for the initial vorticity Xi0 in terms of Xi0n is not empty. In this particular case, it's an example that we constructed. We consider this is proved in the case where the initial vorticity has compact support, solenoidal, and vector field. But it can be generalized to any vector field, actually. This one can be generalized to any generalized vector field, just following the arguments of Pierre Williams in his book in 1996, the famous book on incompressible flows. So this one, if we have Xi, very general result, if Xi is a solenoidal vector field in R3, such that it is divergence equal to 0, we assume that Xi has compact support K in R3, and it is Lipschitz continuous. So if Xi is Lipschitz continuous, then you can find curves gamma in and some weights alpha in R. It's a sequence that converges to 0, such that this Xi is going to be approximated by a vorticity n that is concentrated on these curves. So the sum of the integral between 0, 1, alpha in, this converges to 0, for example, 1 over n, theta gamma in, this is a derivative in sigma. Okay, this is just the derivative in sigma, and this converges to 0 when n goes to infinity. The way you prove this example is the construct this example, you have to use some kind of probability theory that you can construct the law of large numbers somehow. But it is crucial that you have this divergence equal to 0. Okay, compact support you can get away with it, but divergence equal to 0 you can't. So let me just, to finish, let me just say that these results are all, contained in these two papers. One that was the first one, actually, because at the beginning we didn't know how to do it for Euler. All our results were written in terms of, the mean field was just given for a mollified kind of Euler equation. And only later, like 2 years later, we were able to, find the trick to do, the second step to take the delta converge to 0, but that delta that converge to 0, it has to be really depending on n. It's not any. It has to depend on n and the initial conditions. And I will stop here.